And, right. So we stopped yesterday talking about the helicity, and I'm going to continue with that. I was reminded of what people say should be a good colloquium. And if you are going to give a good colloquium, the first part everybody should understand. The second part only the experts in the audience understand. The third part only the speaker understands. And the fourth part, not even the speaker understands. So as you can see, this is the fourth part. Right? I should also tell you that one of the good things which came out of this group discussion meeting, which Axel has been arranging yesterday, is a nice illustration of the Zeldovich rope dynamo, which one of the groups we discovered, which can be operated by any person, any guy with long hair, or any girl with long hair, or having a friend. So when you tie up your hair, you are doing the Zeldovich rope dynamo. So you take your rubber band and you do this, and you make this flux grow. So whenever you do this, you can remember dynamos. Okay? So what I'm going to talk today about is what is called the dynamical quenching model. I will remind you what we said about magnetic helicity and its flux. I will try to motivate how to calculate this flux and tell you the pieces that we know and the pieces we don't know. Up to that will be fairly clean. Then we'll get into murkier waters by trying to see something, to make something about calculating the turbulent electromotive force in the presence of strong magnetic fields or the Lorentz forces. And I will in particular use an approximation which has come to be known as the tau approximation, and in the way in which we used it, I think Eric Blackman suggested, or we suggested, that it should be called a minimal tau approximation. I don't remember now. And then put all these things together to discuss this kind of dynamical quenching, and end with a few questions and conclusions. So let me remind you where we left yesterday. And we said that the good way to talk about magnetic helicity density is to go back to the Gauss linking formula for magnetic fields. And I've just put in some references here. This is, you can find it in a paper by Moffat, long time back. It's not something. Sorry?
Can I ask a question? But linking is just one of the forms of helicity, right? Imagine two unlinked but raised tubes with rise. Helicity is non-zero, but linking formula will give you zero, right?
No, it won't, because if you do this formula for one of those right tubes, you will get non-zero.
You will?
Yeah. Because you can just have an isolated tube with some ride kind of stuff if you want to start off with that. For that thing, you will get mutual links between different field lines at different points. So this X and Y will be both on that tube. If you just have one line, of course, you will get zero. But there is no field of just one line of magnetic field line. As long as you have a bunch of field lines, this will always measure the links between the one infinitesimal flux tube and
there will be no links.
Then there are no links, of course. If it's all completely undried, untwisted, there will be no links.
So you're saying, well, better not to discuss it long, but you bet that if you have just raised tube, one single rise.
Yeah, you'll get non-zero. Because this integral...
Can you recede from the equation?
No, because the integral has to be done with both X and Y on the same tube. So you are always thinking about X and Y in different tubes, not necessary. If you just have one flux tube in the universe, and it's done all kinds of things, it is done to it, and you just integrate on with both the points X and Y on that tube, this will just determine for you the links between the infinitesimal flux tube that you break up this one big flux tube into. And so it will give you non-zero if you have some non-trivial topological thing. Yes. And as I said, you can also write it in the Coulomb gauge as A dot B. And what we discussed was that if you take the average value of this, then because of the fact that the correlation function of the magnetic field has a finite correlation length, if you take a random field, you can transform this d cubed x, d cubed y integrals to d cubed small r and d cubed capital R, and rewrite this 6-dimensional integral as another 6-dimensional integral over d cubed small r and d cubed capital R. And because this integral starts making negligible contribution for small r, magnitude of small r greater than something like L, okay, so if you have an intermediate scale, I can formally let this capital L tend to infinity and get exactly the same answer, and I still have this integral over capital R to do, and this thing in the bracket, square bracket, is what I define as the gauge invariant helicity density of the random field small b. And you can see in the way I have now written it, in contrast to the way I wrote it in my last lecture, that it is some density integrated over some volume element to give you the total helicity. And physically, as I explained, that this is just the density of correlated B field links. And you can see that some of the details in this paper by Axel and myself in that letters. What we would like to do is to take this density and work with it and ask, what is the dynamics of this density? So what we want to do is to determine some kind of helicity conservation equation for this density. And we are interested in looking at fluxes of helicity in space. So this density has to vary from one space point to another space point, which means that you have gone away from a homogeneous system, you have gone to a non-homogeneous system. But we still would like to make it weakly homogeneous so that we can approximate and separate out derivatives with respect to the big scale and derivatives with respect to the small scale. For such weakly inhomogeneous system, it is useful to employ something called the double Fourier transform. Actually, first paper where I have seen this being employed is a paper by Roberts and Soward. There may be earlier papers on this. And the idea is fairly simple. If you have any correlator like this, f of x1 into some g of x2, you Fourier transform both in x1 and x2. So you have a k1, which is the wave vector for this x1 variable, and k2 corresponding to the x2 variable. And now you write this, you make these combination k1 minus k2 by 2, and k is k1 plus k2. They actually correspond, in the Fourier transform, you would have an e to the I, you will have an e to the I k1 x1 dot x1 plus, let's say, e to the I k2 dot x2. And you can combine, if you combine it in this way, you would be able to write it as e to the I k dot r plus I is capital K dot capital R, where small r is what I define to be R1 minus R2, and capital R is the mean position, R1 plus R2 by 2. So it allows you to systematically do the expansion on the large scale in a weakly inhomogeneous system. At the zeroth order, you think everything is homogeneous, but you want to keep at least systematically terms which are first order in the inhomogeneity and second order, etc. If you want to do that, this allows you to systematically do this, and that's why it's quite a nice technique introduced by, I think, Roberts and Soward. So, for example, any correlator like this can be written in terms of a Fourier transform in either I k dot small r, where this is the small k, and this whole thing itself, this phi itself, is an integral over d cubed capital K. So it's just the same thing. I'm just rewriting f into g in this form. For example, these two variables can be the velocity itself, vi and vj, and it will have a corresponding expression here. If you want the electromotive force, for example, you will put a ui and a u cross b, you will put a u and a b here, and the electromotive force itself, the mean electromotive force, will be an integral like this, where this chi is related to this phi function, where f is u, the Fourier transform of u, and g is the Fourier transform of b. This allows you to systematically do your algebra in this two-scale kind of problem. And so the helicity density which I define, it's most convenient to go to Fourier space. So instead of this quantity here, I go to Fourier space, and the small r in the helicity density goes to this k by k squared, and you can convince yourself that this whole thing here, goes over to this stuff here. And I want to work out the evolution of the helicity density and keep terms, leading terms in the inhomogeneities to get fluxes in physical space. So all I have to do is to differentiate, for example, this thing with respect to time. I will get a time derivative of this guy times this, and a term with the time derivative of this guy times this. And for the time derivative of any Fourier component, we basically have the time derivative of the small scale field is related to the curl of the small scale electric field. And the small scale electric field is the total electric field minus the mean electric field. And so it will have these various contributions. There will be a u cross b bar, which would give you all the electromotive force. There would be a u bar cross b. There will be a small u cross small b, which is a nonlinear term, and this average, and there will be a resistive term. So you can imagine that you can just do this fairly systematically, plug this in here, keep each one of these guys Fourier transforms, which will all be in terms of convolutions, then try to keep terms to leading order in capital K, so that you get all the terms up to derivatives, let's say, in capital R. Okay? So I won't really go into all those things, but if you plug that in, you plug the previous expression and take the time derivatives and write down the evolution of small h in terms of time, you get the following terms. You get various combinations of E and B, the electric field and B. And here I have already kept terms only up to this is at present an exact term. And there are various combinations of capital K which has come because this term, K by K squared, okay, when I take the time derivative of this one, minus K plus capital K will come here, and similarly plus K plus capital K by 2 will come here. And so at present this term is absolutely exact. So far no approximations have been made. But because in these terms there is already a capital K which corresponds to a large scale derivative in R when you go back to physical space. If you only want leading terms in the derivatives in capital R, you can actually forget about the fact that these depend on capital K. This term doesn't have a capital K, but it's exactly the same term as you had before. You were just small e dot small b average. So the first term here, which I called as A1, is exactly minus 2 small e dot small b average, which you get in a normal helicity conservation equation when you have all the fields to be homogeneous in space. And as you can see, because of the fact that the electric field had all these different terms, and you are dotting it with small b, term will drop out. Okay. This term, importantly, will drop out because this is perpendicular to small b. And when we dot it with small b, this will drop out. When you take the average, this term will drop out. So you only have contribution from the resistor and this u cross b dot small b. And that you can rearrange because if you look at minus u cross b bar dot small b, an average of this, you can write it as plus b cross u dot b bar, and then you can write it as b bar dot u cross b, and this is nothing but the electromotive force. So doing that, you basically, these two terms will give you minus 2 times the electromotive force dot b, minus 2 eta j dot b. The other terms have dropped out. The important thing is that the nonlinear term has dropped out. If the nonlinear term had not dropped out, you would get a triple correlation in the small scale fluctuating quantities. And if you have a triple correlation, this is an equation for the 2-point correlation, and you've got a triple correlation. In normal turbulence theory, then you have to write an equation for this triple correlation. Then you'll get a 4-point correlation, and you have a closure problem. The magic about magnetic helicity, which is why it's very important, and if I try to do this with current helicity, I would not have been able to do this, is that such triple correlations drop out on the leading terms, because this term does not depend upon large k, it is the term which survives under homogeneous conditions. And the triple correlation drops out, and you get exactly minus 2 e bar dot b bar minus 2 eta j dot b. An important remark is that now you do not have a volume integral. If you saw my earlier expressions of the whole thing, there was this one more average which I had put here. That average represented the integral over all volume for the small scale helicity. Because now I am working with the density of helicity, this is the actual value as a function of capital R still. So that has not gone out here. There's an integral over d cubed small k and capital K, but still a dependence of capital R. So firstly, this is the local helicity generation. Local generation of helicity density due to the turbulent electromotive force parallel to the mean magnetic field. And similarly, there is the local dissipation of the helicity density. If you look at the other two terms, then these are the terms which lead to the fluxes of helicity. Because there is a capital K here, so you can imagine that you can write this capital K times e to the ik dot r as an R derivative of everything without the capital K. This is a standard trick, and so this will be the capital R derivative of various things, and these will be corresponding to the fluxes of helicity. But you can see that they have a very complicated tensorial structure here. They are not simple. And you have to do a lot of work to find out what they mean. First thing you can see, you can look at, everywhere the electric field appears, and the electric field has various pieces. It has a piece depending on B bar, it has a piece depending upon U bar, it has this nonlinear piece. This piece will never trouble you because when you take average, this is already an average, so this times the fluctuating quantity average will be 0. This will not trouble you too much because it's a resistive quantity in the flux, but you can keep it. These two pieces still lead to 2-point correlations because you plug them in into these expressions. When E is U cross B bar, you still get a 2-point correlation between this U and that B. When E is U bar cross B, you get a 2-point correlation between the B and the B. And there's an average quantity there. But this piece, when E, the part of E, which is small u cross small b, now will give you a 3-point correlation in the flux. So although the helicity density at the lowest leading level has an evolution equation which does not require any closure to evaluate, the flux can require a closure to evaluate all the pieces. This piece will require a closure to evaluate. And what you look that.
Somehow, so what's the difference between the first term and the other two? That in the first you have EQ, BQ, and here you have EQ, BJ, right? No, you have EQ. You just explained why the first term doesn't involve triple correlation.
Yes.
Right?
Yes. Yeah, it doesn't have any of these complicating factors, the first term. Even in the third term. Third term, there is this k dot, the first term can be pulled out of the Fourier thing and written in space as E dot B. The third term cannot be done like that.
No, it's okay, but I'm talking about triple correlations.
Yes. So the triple correlations, there will be triple correlations in both these terms.
Why not done in the first? You just explained why
Oh.
the first will not involve them.
Because the Fourier transforms of E and B are not perpendicular to, I mean, when you take U cross B, there's a convolution here in Fourier space.
Yes. Okay, good, okay.
And
Yeah.
you have know where eta is your main relation. Does it mean that you...
No, eta is here. Eta is in the electric field. I have put it all in terms of the
It
electric
comes in if you... Yeah.
Yeah. Yeah. So eta comes in the electric field. It is that.
Yeah.
Okay. So, from this term, small u cross B bar term, you get fluxes proportional to B bar itself. So, in fact, somebody in one of the group discussion was asking me, how will you transport the helicity density if there is nothing on which to transport it? Okay, so one way is if you have a mean field connecting various places, and then this term will correspond to such fluxes. On the other hand, this term, U bar cross B bar, can transport helicity along these U bars, governed by what U bar does. So this is what we will call the advective flux. In fact, this is something which was always emphasized to me by Anwar from time immemorial, but we never worked on it until I could derive these equations at some level.
Which was a mistake.
Hmm?
Which was a mistake.
Yes, I never believe you, Anwar, until, but you are also obstinate that too, so it's okay. It's a mutual. This term I will not talk about at all. It is something which we have not done too much any work on because it requires a closure, and by the time all this was done, we got exhausted, I think. But it's worth revisiting at some stage. So let's look at these two terms. So I'm not going to go through the algebra of evaluating it, but the term proportional to B bar gives two types of terms, which have been discussed earlier in the literature. One type of term was discussed by Ethan Wishniak and Cho long time back, and which we call the Wishniak and Cho flux, and we just kept rediscovering it in various avatars in that sense. And what I will write it down more, it depends on this chi, because it involves if you look at this, there's a U here and there's a B here. It involves a U-B correlation. So this is a flux which depends upon the mean magnetic field and the turbulent electromotive force itself, some tensorial part of the turbulent electromotive force. Whereas this only involves the mean velocity field and the magnetic field itself. That's why it comes like an advection. So if you put everything together, at the leading order, you get a local helicity conservation equation where the density of helicity, d rho by dt, plus the divergence of a flux goes as the volume generation. These are all local terms. And the flux itself consists of various pieces, these two pieces which depend upon v bar, this piece which depends on the bulk velocity, and this piece which depends on the triple correlation. These are the only pieces which appear. The previous equation, as I said, was exact. There's no approximation there. So the simplest flux is, of course, motivated by Anwar, and it appears absolutely naturally when you take this term in. And they also make one further approximation that the field is isotropic. If the field is non-isotropic, you get the advection of a non-isotropic kind of correlator. And it is, as you should expect, that it itself is the helicity density times the mean velocity. So this part is absolutely natural. You get dH by dt plus divergence of h u bar, which is how you always see any conservation of a density. You always see, like continuity equation, you'll have d rho by dt plus divergence of rho u, or momentum density conservation. You'll always see it that way. And it's absolutely natural. That's the simplest flux. It doesn't depend upon anything except the fact that you can throw out helicity from your system or bring in helicity from somewhere else. It's helicity density. These fluxes are more complicated to imagine. In Ethan Wishniak and Cho paper, you can find a picture. And it's very difficult for me also to look at that picture and understand something, I think. But as I said, you can derive it, and I'll show a different form for this. It depends upon the electromotive force correlators. And Clearin and all also had some kind of a flux. Okay, that's where Roberts and Server thing has come in. So in the presence of these helicity fluxes, I think this keeps, maybe I'll just take it out.
Maybe if you turn it up, it'll slow down.
Yeah. So in presence of these helicity fluxes, in the stationary limit what you have is that this turbulent electromotive force parallel to the mean field could be balanced by the divergence of the flux. A remark which I would like to make is that one may think one has escaped catastrophic quenching by having helicity fluxes, but it is not guaranteed, because it may be that all the different bits of the EMF, all kinds of different tensorial correlators of the EMF are all suppressed, in which case these two fluxes will also be suppressed, and this will also be suppressed. It will all be consistent. One thing which breaks this is the advective flux. So the fact, if you have the advective flux, then you are absolutely guaranteed that you have a flux which is not quenched. It's very simple, because you are just taking things, carrying it along and putting it somewhere else. But if you do not have this advective flux, I do not know any way to demonstrate at present that you can't have a complete quenching of everything, of not only the EMF but also the fluxes. You had a question?
Yes, for example, of the sun, we believe that the meridian flow is like one cell. So in this case, there are not total fluxes. So
yes, so that's why she said about coronal mass ejection, which has to be demonstrated, I guess. But that is Axel's idea, that if you have the CMEs, they could carry away the advective. If you bring the helicity somehow to the surface, even if it was generated somewhere else, then the CMEs could carry it away. Right, Axel? That's the basic idea.
Kind of, then may I ask a question? In order to understand it better, you can write down the original relation for the magnetic helicity. Time derivative A dot B equal to several terms plus divergence. Under the divergence you have A plus E plus B phi. And you can use the same for the little a and little b, and this means the fluctuations. Then you arrive at this equation you have in the first line,
Yes.
and F is just A cross E plus P E. What you have done in a, I don't know what way, is derive expressions for A cross E
Yes.
plus P phi.
I would claim that I've done something more. And that something more is that whatever you are writing A and phi are dependent on the gauge. So you are not guaranteed at the end of the day that what you have derived is correct. And if you make a gauge transformation,
And I have made a mistake. I started from an equation which is right, and I can honestly calculate A cross E.
yeah,
plus P phi.
but to define A, you have to adopt a gauge.
So,
To define the vector potential, you have to choose a gauge.
yeah, and you have.
I have not chosen a gauge.
You have not.
No. Yes.
Because he was just working with the density of linkages.
Yes.
You have adopted a gauge.
If you want, but okay, I should make that remark also. If I take the Coulomb gauge,
Yes.
okay?
But you have a reason why you have done it.
No, okay, but there is something more involved, which is what puzzled me, and maybe puzzles me even now. If I take the Coulomb gauge and just blindly take this double Fourier transform, under homogeneous conditions, it doesn't change from this definition that I have given here. But under weakly inhomogeneous conditions, what happens? This k and this k, small k here, will reflect one of these coefficients because I have a at x and b at x. So it will either be, you can take it as small k plus capital K here by small k plus capital K whole square here. Now, when capital K is neglected, small, it doesn't make any difference. Even at the first order of capital K, that extra term that you get from whatever is written here turns out to be 0. But higher order, it is not 0. Which is why when you have a weakly inhomogeneous system, it is a bit tricky to say exactly what, but the closest it is to Coulomb gauge, of course. So there are two remarks. The closest meaning of the helicity density is to just work in Coulomb gauge. And all other gauges are artificial because they are just something which you went because you wanted to integrate over the whole universe. But you do not have the luxury of integrating over the whole universe, but you have a random field. So you have a correlation length and you want to define a density. So if you are working the Coulomb gauge, there is no problem in that sense at the leading order. But I am not able to demonstrate that it is the same as this. But this came absolutely naturally as I was explaining. So we make this remark in our paper, but we just leave it at that at present. Yeah, so Karl-Heinz, I think.
If you have at the end relations between, say, observable quantities which have really a physical meaning in contrast to vector potential, then it must be without interest which gauge you choose.
Not if you are dealing with density of helicity, because helicity is observable, but you want to deal with fluxes. And what is this flux? So I think you should do this exercise of trying to work in different gauges and make up predictions for this, because we've struggled for quite some time. Even now, I think Axel in his simulation wants to make sure that whether his fluxes are independent of the gauge that he chooses. And it is not obvious that they will be. Isn't it, Axel?
Yeah, in the one-dimensional mean field models or the simulations where we do planar averages, it actually turns out that in the steady state, 3 different gauges give the same fluxes for good reasons. Exactly the same fluxes.
Yes.
So in some cases it has been checked and there actually it was working without ambiguity.
But you have to fix some special things then.
And then on one end there has to be a perfect conductor which really fixes everything on one end of the domain.
your little h is not, how to say, a well-defined quantity.
Why?
If you define it by little a times little b, then the gauge of a has influence.
But I don't define it that way.
But he is not doing it.
I'm not defining it that way. Maybe.
On his caves, he never uses A, right?
See here, this is the definition of the little h, which has only the magnetic correlators, which is only the field correlators. So it is not defined using A.
Okay.
Yeah, I mean, it took me a long time to appreciate that there is something non-trivial here. And I think one has to think about it. Yeah. So as I said, yeah, so far, whatever I have done is absolutely doesn't have various arbitrary things except that I've just used some definition and I've given you an equation. And I've said it's plausible that in the presence of such fluxes, you will get a non-catastrophic quenching of your turbulent electromotive force. And somebody else in the group discussion, in fact, raised this interesting point, but okay, then where is the Lorentz force going to come in at all? Okay? The helicity conservation, as I was explaining to that group, is a conservation law which is like a constraint on a system. For example, if you have a dynamical system and your energy is conserved, it is a constraint which the system has to satisfy. But it does not determine the dynamics. Sorry.
As Karl-Heinz was stressing, it's not an independent constraint. For example,
Yeah.
the energy conservation, it's built into the Navier-Stokes equation.
Yes.
If you have solved Navier-Stokes equation, in principle, there is
Yeah.
no need to impose
Yeah.
additionally.
So,
energy
yeah, I'm coming to that.
conservation,
Yeah.
It's exactly what I'm coming to.
On the same level as energy balance.
Yes. So if you are able to solve for the actual magnetic field evolution, small scale, large scale, whatever, don't split anything. Just take the induction equation and the momentum equation and solve for everything. You don't have to worry about helicity. It will be automatically conserved. But the fact that we want to do mean field theory means that you may be not conserving helicity if you are just solving the mean field equations arbitrarily. Because you are not taking care what you are doing with the fluctuating fields. You are not solving for them. You are not treating the dynamics properly. Or the fact that you want to understand why your system behaves in a particular way. That why do you have, when everything seems quite okay, why do you have catastrophic quenching, for example, in the box, periodic box simulation? If you want to develop a conceptual understanding of this, or to develop understanding of what possibly you could do to prevent such things, and what are the escape routes, then the helicity conservation equation plays a useful role. So it is not a substitute for solving the induction equation in its full glory.
But quenching is not a matter of the induction equation, but quenching is reduction of the velocity field by the Lorentz force and described by the Navier-Stokes equation. You
Yes.
cannot derive it from the...
Yes, I'm not deriving it. I think you should wait and be patient.
But the point, no, but we know exactly where the point is, where it comes in. It comes in through the Pouquet, Frisch, and Leora equation for the alpha effect.
That's why I'm saying patience.
What? You come
That's
to
why I
that.
said patient. I'm going to come to that.
Yeah.
Yes.
So it does come in exactly at that point.
But Kala is absolutely correct. You are absolutely correct. But I'm wanting to be a little bit like you, making statements which are not completely now wrong yet. Okay? Which is a chess player. I shouldn't try to be that. So up till now, there are no wrong statements that I am making. They may be superfluous, but they are not wrong. Okay?
Now start making your own statements.
Yes, now I will start making wrong statements. Because if you want to put it to use, then you need to ask what the Lorentz force does to the turbulent diffusion coefficients. Because of course, this gives you a conceptual understanding of what's happening in some of these simulations and why you could have landed up with quenching and how you could escape quenching. But if you want to actually use this, then you have to go to the dynamical question. That's what I'm going to come to now. So if you want to use this helicity conservation equation of any particular way, then you have to ask, how do you find the turbulent electromotive force under the influence of Lorentz forces? So this, as Carl has already explained to you in his lecture, is a difficult question, and we can make general statements. So you go back to the equation for the small scale field, you go back to the equation for the small scale velocity, and now you have extra terms due to the Lorentz forces, which depends on small b. There are of course also extra terms which depends only on the mean field, which I'm at present thinking of as small compared to these terms, which depend upon small coupling between b and b bar. You have external, you may have an external forcing, or you may just have a decay, or you may have some instability going on in the system, in which case you do not necessarily have an external forcing. And you have all kinds of nonlinear terms. Now on top of the nonlinear term, the pain in the neck term in the induction equation, which is of this form, you have a pain in the neck nonlinear term in the momentum equation, which consists of various quadratic quantities u dot grad u, b dot grad b, gradient of b squared, etc. So as I kept emphasizing in my
what the dash means here?
Dash is Karl Heinkel's notation. When you put a dash, you subtract out its mean.
Okay.
It's his notation. And as I emphasized, that even calculating this electromotive force in the kinematic limit requires a closure. And obviously, if you are trying to calculate something in the nonlinear limit, it will require some closure. And closures are things which are, you can argue about forever and not get anywhere. You make it, if it works, you are happy. If it doesn't work, you look for something else. In any of the nonlinear systems that you study, when you have to make closures, it's absolutely impossible to justify. You can only motivate a little bit, but you can't really justify or derive. So either you never do it in your life, or if you want to do something, you do something. So kinematic limit, we already went through this algebra, and I won't repeat it. So this closure which Karl-Heinz also mentioned, in fact, he's also first author of this paper, which is one of the papers which derives this kind of thing, which I've called this minimal tau approximation closure. What it does, you start with an equation for the derivative of the electromotive force. Now this is also something which is okay. Turbulence community always starts when they want to derive an equation for the two-point function, they'll always start with its derivative. Then you plug in your equations where the derivatives appear, and then you will get your nonlinear terms. So the derivative of the electromotive force will be given by u cross b dot plus u dot cross b. Dot denotes the time derivative. I've just gathered together the important terms. In p dot, there are nonlinear terms which are all being dumped under this n here. There are terms it depends upon b bar itself, which are written out explicitly. Oh, there's a g here, so I've not yet dumped it there. So the g cross u are all the nonlinear terms. And I've not even kept the u bar here. That's why I'm saying I'm now becoming dirty. The important terms in b, u dot, which depend on b bar, are all the Lorentz force terms, okay, cross small g. Then there could be a forcing, and there could be the nonlinear term in the momentum equation. You can simplify these terms. So this is exactly what we discussed as a turbulent diffusion, advection of b bar by u, and the electromotive force due to that. And this is exactly what we would have discussed as the alpha effect, except there is no integration over time, 2 times here. which always worried people who have always dealt with it in this way, including Carlyle, who always was concerned about this fact that there is no two-time integration here. But there is nothing wrong in taking derivatives and doing this. The thing which will come questionable, I will come to later. So that's why I called it alpha twiddle here, and not the alpha effect, because it is actually just the average of the kinetic helicity in the isotropic limit. This Lorentz force term gives a new term. You would have imagined that a term like B dot grad B bar would give you something like the magnetic alpha, and B bar dot grad B will renormalize the turbulent diffusion. But there's an important difference here between these two. There's some gradient of pressure and there's a divergence of U is equal to 0 constraint on the whole system. And it turns out, and I've done it in different ways. Magically, the term due to the pressure and this term, the contribution to the turbulent diffusion due to the small scale magnetic field, they cancel. And in this approximation, there is no correction due to the small scale fluctuating magnetic field to the turbulent diffusion type of term. So that remains as 1/3 U squared, dominated by this term here. And all the small scale magnetic field does is to introduce a term like the alpha, but now governed by small p's. Instead of U dot omega, you get J dot B. I'll discuss this in a bit more detail later. So what it seems to do, and of course then you get a force correlation, FB correlation, and nonlinear term times B correlation.
Somehow your expressions for alpha tilde and beta t tilde systematically log tau,
Tau,
right?
yes, there's no tau yet.
What do you mean?
Because they are all evaluated at the same time.
Oh, okay. Mm-hmm.
There's no tau yet. They're all evaluated at the same time. The tau will come in now. So originally many of these authors just put the F cross B to be 0. Or actually Carlyle just absorbed it into this term. You just absorb. When you are discussing in your lectures, you just put it all together as one thing. Right?
No, I switched up.
Okay.
Not before.
Okay, right. But you can show under certain restrictive things, which I'll mention later, that sometimes the F cross B correlation does turn out to be 0. And we were very surprised to find this under some simple systems of low magnetic Reynolds numbers, which are more exact calculations. Now, what do you do with this nonlinear term? Because this has got 2.2 magnetic fields and velocity field. This also has got U and B, and you're crossing with another guy. So there's a 3-point function here. The drastic closure, which was suggested by, I think, maybe Kriorin, Robchevsky in other contexts, and then Zachman and Field in some other context, and Axel and I just worked it out in great detail in following the paper of Radler, Kriorin, and Robchevsky, is that you say that all these nonlinear terms just contributes a damping of the EMF with some relaxation time tau. Okay. What do I mean by that? The idea is that suppose there was no B bar in the system, so you imagine that there are no mean fields in the system, then in this isotropic kind of situation, homogeneous situation in this case, there should be no mean electromotive force generated. So it is the presence of this B bar which will lead to a non-zero electromotive force. And so if you had a system where there was no B bar, you should get just d bar by dt should be just damped to 0. The E bar should be just damped to 0. That is the kind of simple motivation. So if you had none of these B bar terms and you just had this term, then you will have a simple differential equation d bar by dt plus E bar by tau equal to 0, we just exponentially damps E bar to 0. So if at some stage you switch off the mean field by somehow, then the electromotive force should disappear. That is the requirement. And so there is a tau which is now arbitrary. So this is absolutely arbitrary. Mathematically, it's what you would call a closure hypothesis, something which relates the third moments to the second moment. And I will come to discuss checking this, but this is the assumption which is made. So now if you plug this in, you will get here n is equal to minus E bar by tau, and you can see that the steady state solution to this, I mean you can keep that time derivative, but if the tau is small enough, then your E bar would be driven to a steady state. In the steady state situation, your E bar would just be given by this tau alpha twiddle B bar minus tau eta twiddle curl B bar. So it looks exactly like your normal alpha effect and turbulent diffusion, except for the important difference that now the alpha effect has got an extra contribution from the current helicity. Now I will argue this because it's dirty. I am going to argue it in 3 or 4 different ways. Whenever something is clean, you only have to say it, and then everybody accepts. Whenever something is not clean, you have to say it in 4 different ways so that people think it may be plausible. So let's first look at it as it is here. Now this fact that the alpha effect could get renormalized by a term proportional to the current helicity is not a new thing. It was derived in a more sophisticated closure called the EDQMM closure, standing for eddy damped quasi-normal Markovian closure, by Pouquet, Frisch and Lora, I think, in 1976, 75? You put 75? 76?
Yeah, there's 2 papers.
Oh.
Frisch is 75. This is
Okay,
76.
this should be 76.
Yes.
It should be 76 in Journal of Fluid Mechanics. So this is a kind of standard closure for fluid turbulence, which of course again is hotly debated, you know, whether it is correct, this, that and all. Any closure will be hotly debated. Okay. And then Pouquet et al. Were the first people to try to adopt it to magnetohydrodynamic turbulence. And they derived both these results, that the alpha gets renormalized by terms proportional to the current helicity, and the turbulent diffusion does not get affected. Now if you remember my previous lecture where I introduced the ambipolar drift effect, that certainly changed the turbulent diffusion. But that changed the turbulent diffusion because I did not impose the condition that the divergence of the ambipolar diffusion contribution to the velocity is 0. And in the physical ambipolar diffusion, this divergence is not 0. For example, you can have ambipolar diffusion comes about when there are neutral particles and the Lorentz force acts on the ions but not on the neutral, so kind of escapes from some neutral region. And there the divergences are not 0. So that's okay. So it is an accident, of course, that it is exactly 0 here. We are always amazed by it. And you always have to check it a couple of times, and I've checked it different ways, and it's always 0. Now, you could ask, okay, so before going into anything else, so this is the first way in which I'm going to say that this is not so bad, because Axel was trying to check this tau approximation in his simulations. I'm a co-author, but I'm a co-author because I'm an audience to Axel's simulation. Okay? And I just sit with you, Axel. Of course, I read the paper, of course. So what is plotted here, so what Axel has tried to do is to run simulations and then impose, these are before the test field thing. So these are imposed constant fields, and measures in the simulation various quantities and tries to see whether there is a relation like alpha effect can be written as a kinetic alpha, which is just u dot b, which you can also measure in the simulation. Sorry, u dot omega, which you can measure, and a magnetic alpha, which is j dot b in this form. These are just coefficients just left free to begin with, so that in principle the time, the tau associated with the kinetic helicity and the magnetic helicity need not be in general, and you can try to see whether you can measure this. And what is plotted here is the Strahl number, which is tau expressed in a dimensionless form in terms of the turnover time in the turbulence. This is the forcing wave number, this is the RMS velocity of the in the fluid, and this is the tau. And what you can see for various cases here, okay, and this x-axis is a function of the magnetic Reynolds number in the simulation. The first result, which was very surprising and pleasant, was that tau is positive. Because when you make such a closure, and there are all kinds of dirty terms, okay, you don't even know whether something which you are going to, this damping is going to damp or not. Okay? And so the tau which you inferred is positive. And secondly, in most of the cases that you can see here, it's of order 1 in these units. So the tau is of order the correlation time of the turbulence.
Just a quick one. That alpha k, the alpha twiddle k that you've got in there, that's the bit that comes from the u dot omega. But that's to be interpreted as the u dot omega when there's no field, is that correct?
No. In this derivation, good that you brought up this point. In this derivation, we never said that u, omega, j, b are some zeroth order level thing. Because you are taking time derivatives, these are the actual u, actual b, actual j. This is what we were discussing the other day. Yes. It's just to be interpreted as whatever you get. In fact, in the simulation, it's once you put the field, it's anisotropic. U and it's not exactly u dot omega, it's what Axel wrote down the other day. Ux, comma, y,
Yes.
Omega z. It becomes even anisotropic. So I'm just putting it qualitatively there. Yeah, it is the actual u, whatever you see. Because when you take this derivative, see the drastic step you have done is here, when you make n to be just this. But all over here you have not done anything.
So I'm slightly confused here. I mean, because Karl Heinz said, yes, the quenching comes in about because it affects the omega and the u, yes? I mean, the Lorentz force changes the omega and the u, yes? But in your formula there, it appears that it's not coming in as changing the u and the omega, it's coming in as an additional term.
Yes.
So
in fact, I'm going to say something about
different from what Karl Heinz was
yes.
saying.
Why?
I'm going to say it's not this. It's not
u
very
dot.
different actually.
It comes in through the u dot, the second part.
Yeah. He also had this term.
Yes.
The question was whether you put a zero there or not. He wanted to put a zero there, and I was saying, don't put the zero.
But remember what I said in my lecture. If you consider second order correlation approximations, that means the nonlinear terms in your equations are small. Then you get a relation for alpha which contains u and curl u and no j and b. And the u and curl u may depend on the magnetic field. And you can have four quenching from the u curl u. So I think
Yeah, so I'm going to say something about that also.
this is not a term which primarily describes the quenching. This J. You can have the quenching also from the what you say.
No, you have both. You may have both. I'm going to come to a system which I have not really described in full, but where everybody can agree and all the results will be the same. I'll come to this.
I think there's another remark. The fact that there's quenching is, of course, nothing new in the community. Quenching has been done since 1970 by Moffat and then Rüdiger in 74. But what we are talking about is catastrophic quenching. That it means a quenching that is actually dependent on the microscopic magnetic Reynolds number. And it matters whether it's 10 to the second, 10 to the fourth, 10 to the eighth, or 10 to the sixth. This matters. And this is the quenching which is not borne out by most theories. And the only theory that actually reproduces this is one which involves magnetic helicity conservation.
Yes. But I'll come back to your question again in a different context here. Right now there is no, this is the actual velocity field, an actual magnetic field. And what Axel is measuring here is the actual velocity field and the actual magnetic field, but an anisotropic version, because once you impose this B, you get straight away anisotropy. So the only thing which I would say is that I think maybe Axel, you need to check these points more now if one is more interested, because as you can see there's a slight dip here. But even that it works up to whatever Reynolds number of 100 or something is interesting, that you made this absolutely drastic closure approximation and you're checking it and something works in this. So it's based on this physical idea that if you did not have the mean field, your EMF should drop out, should decay to zero. That's why you did this kind of thing. So let me make now remarks about this. So if you want to now address and incorporate, do mean field theory. Again, let me repeat, if you do solve the actual induction equation, you have nothing to worry about. You just solve the induction equation and you'll be happy. As your computers improve, you will solve it better and better. And maybe in about few hundred years, you will have enough resolution to solve it for the actual sun. And that's it. We should just do that, actually. But if you want to develop an understanding of what happens using mean field theory, or you want to understand something as to what setups that you should use to solve your equation, then you can look at this dynamical kind of quenching model. The idea here is that you solve the dynamo equation, but you add into that this constraint from local helicity conservation. So the dynamo equations are for the mean field. So it is not guaranteed to conserve the small scale helicity, because you've just thrown that out as you have done some closure. But you impose this as a constraint, the helicity conservation. To make practical use in the helicity conservation equation, you have magnetic helicity, and you have to relate it to what changes your alpha effect here, which is the current helicity. So you take a form for the alpha to be a kinetic plus a magnetic alpha, with the magnetic alpha to be proportional to J dot B. So we have already raised these two questions. Is there such a magnetic alpha? And what is tau? So when I actually gave such a talk in 2004 in the Newton Institute, the same question came up. Is J and B the actual field or not? And if it is the actual field, then it must be wrong, because the induction equation is linear in V bar, and everything about the electromotive force is contained in the small scale velocity, but the small scale velocity may be influenced by Lorentz forces. So this is something which has been, which is a philosophy which is there from Karl Heinz or from Moffat, Keith Moffat, and this was exactly the question which was asked. So we decided to look at a simple system where everybody will agree about the answer, because the closure there is very simple. I have not given you the details, but I can refer you to a paper. This is a paper by Sharanya Sewell, Axel and myself, where we look at a system which has got a small magnetic Reynolds number and a small fluid Reynolds number. So everything can be calculated, because you can say the resistivity dominates and the viscosity dominates. It has nothing to do with astrophysics, but you can clarify all the conceptual questions which you can ask in this system. So if you have such a system, then you can use first order smoothing in the induction equation. You can also use first order smoothing in the momentum equation because the Reynolds numbers are small. All the Reynolds numbers are small. Then it turns out you can write your alpha effect. Now you can also calculate everything because you have very simple linear equation. You can calculate U, you can calculate B. You can calculate alpha directly as U cross B average in this system. But if you just stuck to the induction equation, you will first solve for the small scale magnetic field. Okay. Then you will take the U, the actual U, cross it with the small scale magnetic field, and you'll get the alpha effect. Something which people don't do normally, but you could just stick to the momentum equation. Then you will first calculate the U from the momentum equation, and then cross it with B, the actual B, and calculate the alpha effect. So there are 3 different methods of calculating the alpha effect. And because this system is exactly soluble, you have to get, by construction, the same alpha. So it turns out that you can write the alpha either as an actual UU correlation, which is what you are saying and what you say. You can write it as a sum of a BB correlation and an FB correlation. This is the actual B correlation. And you can write it as a UB correlation also. When you write it in this form, okay, and I should have probably put those slides up, what you will discover is that there are 2 terms to the alpha. One term which is a modified U correlation, modified helicity by the Lorentz forces, kinetic helicity. And one term in this particular context, which is not the current helicity but the magnetic helicity itself, because you are working with a small magnetic Reynolds number system where the operator del squared, an extra del squared appears, which converts, takes out a k squared from J dot B and makes it into an A dot B. So we showed in this paper that this confusion about whether you should use actual U, actual B or not is a question of semantics. You can use the actual U, at least in this system, but you can also decide to use a U which is modified by Lorentz forces, added to that a current, in this case, a magnetic helicity term. Okay. So this kind of encouraged us to say that, okay, one way, so this is my second way, saying that having this magnetic helicity will affect the alpha effect. And if you could get rid of it, you will do something good. Let me also mention the another point, which is that you can do the same thing in 2D, and this is actually much simpler, and it's been emphasized a lot by Pat Diamond. That's the Isaac Newton Institute talk of it. And in fact, his talk was called Placating Proctor, because Mike Proctor raised this issue at that time. And in 2D, what you get, instead of a renormalization of alpha, you get a renormalization of the turbulent diffusion from just depending on U squared to a U squared minus B squared structure. And it is very similar to this renormalization of the alpha effect. So, the net thing which I want to say is that basically it is good to transport away magnetic helicity by some flux. If you do that, what will happen if you do not do that is that as the mean field grows, the system conserves helicity. There is one sign of helicity in the mean field or large scale field, the opposite sign in the small scale field. Associated with the small scale field helicity, there are Lorentz forces which oppose the alpha effect. And you can of course see it in one of those pictures, which if I go back to, maybe you can see, maybe you have experienced it best in this picture. Anwar. Sorry. When you try to do this, you must have felt the Lorentz forces, right?
Oh, very strong.
Because
it was pulling this stuff out of my hands.
yes, right. Because what we are talking about is just the back reaction due to the Lorentz force. When you try to write something, which is the kinetic alpha, you produce these twists. And if the twists become too strong, it will just try to unwrite it. And this is exactly the magnetic alpha. The magnetic alpha is a consequence of the Lorentz force due to the twist that you are building up in the field, or due to one sign of helicity that you are building up in the field. So of course, I have given you now the third or fourth argument, that physically it is nothing, although you can argue ad infinitum about various closures and how you get it. This is obvious that whenever you are trying to do this twisting thing, you will have the twist that you introduce will be the strongest part of the Lorentz force, because it will have the smallest scale, and that will try to untwist the whole thing if you just left it. And if you took bath with one of these pipes, or if you are playing around with one of these hose pipes, you will feel these forces. So, the way in which one of the mechanisms by which the large-scale dynamo tries to grind to a halt is that as you try to produce mean field, you necessarily have to invoke both colloidal and toroidal fields to produce the mean field in your mean field in the dynamo. And so you necessarily are producing mean field helicity, and so you are necessarily producing small scale helicity. The smaller, because of the small scale, the Lorentz forces associated with it are stronger and will kick in much before your mean field becomes correspondingly strong. Because as I said, for the same A dot B, or for the same magnetic helicity, the J's are up by a factor of 2 powers in the scale. And so you will necessarily produce a back reacting alpha effect, which will try to untwist you. So, several different ways of saying the same thing, because I can't prove any of them to be totally correct. But all of them look, I can make it sound plausible, of course. Then if you accept this, you say that you take the mean field dynamo equation with an alpha effect, but the alpha now you add to it a magnetic alpha. And this approximation, you don't do anything much to the turbulent diffusion coefficient. Then you look at the helicity conservation equation, and you try to relate the helicity to the current helicity and the magnetic helicity by using some scales of the field. And you convert the helicity conservation equation to a dynamical equation for the alpha magnetic, where the alpha magnetic involves a J dot B, and the helicity was something to do with A dot B in some rough way. And now your system is kind of closed up to this level, but of course it's approximate. It's closed in the sense that the back reaction here to the alpha effect comes to the magnetic alpha, and the magnetic alpha is governed by an evolution equation in terms of the mean field, except for this flux, of course. So if you do not have this flux, okay, then you can re-derive for yourself that when the magnetic alpha goes stationary and the flux is 0, your total alpha effect can be re-expressed in terms of the original kinetic alpha. And you have this Rn dependent factor in the denominator, so that even when the mean field is very small compared to the equipartition type fields, you have some catastrophic quenching of the alpha effect. But in the presence of these fluxes, this need not happen.
So, there are 2 RMs, right, in this formula?
2 RMs?
Upstairs, he means.
This one. So that has never been made to work.
No, it does work, of course. It means that in the case of a periodic box, you reach equipartition and even super equipartition values. That's exactly because of this term in the numerator.
Oh, yeah.
Because
Okay,
then in the periodic box, the current is just as big as B is,
yes,
because it's a Beltrami field.
Yes.
Under non-periodic conditions, you don't really have that, and then
It
it's not so big.
works if you have a finite, if you have boundaries and all that, then it doesn't work.
But you don't escape the fact that the alpha dot to be negligible, is you can't do that in that case.
Yes, of course, this whole approximation is not correct, Anwar, to begin with. Alpha dot is 0.
So it leads to a slow saturation, very, very slow saturation, but it does lead to a super-repetition in the end.
So here let me show you some results of such an exercise. For the first paper which solved these things together was already papers by Kliorin, Robchevsky, David Moss, and Dmitry Sokolov in the early 2000, which solved all these equations together. Axel also did some. There was a paper which we wrote, I think,
2005. Yeah.
Yes. But I put this first because this involves the advective flux, which Anwar had been telling me since 2004 or 3 or whenever. But
in Durham, meeting in Durham.
Yeah, some long time back. And since I never believed him, I prevented him from writing his paper either.
Yeah.
So then finally I believed that that could be something like that, and then I was with Axel, and then he solved all those equations. And I had a terrific time because Anwar wants everything in length, and Axel wants everything in wave number. And there are these factors of 2 pi floating around in all definitions. 2 pi cubed.
You got them all out, I thought.
Yeah. You won, of course. Right. And that's why everything is k, and these numbers are all of order unity and not the numbers that we are used to in the galactic dynamo, which Anwar will tell you, of course, later. And so what you can see is that this Cu, okay, so this is an alpha omega dynamo. These are the parameters for the omega effect and the alpha effect in some dimensionless form. The Cu is the amount of advective flux that you have, whether you advect away helicity from the system or not. So this is just a 1D calculation where you put some advective velocity out of the system. And if the advection is 0, then initially the mean field grows, and as the mean field grows, it's producing magnetic helicity because of helicity conservation. And because it's producing magnetic helicity, the alpha magnetic grows, and the alpha magnetic opposes the alpha kinetic. And after a certain point, the alpha effect becomes subcritical, so everything decays. And actually, if you wait long enough, longer you have to wait, depends on how long you have to wait, depends on the magnetic Reynolds number. After some time, if you wait long enough, the alpha magnetic will decay because of just microscopic diffusion, the magnetic helicity will decay, and so current helicity will disappear. And then the whole thing will come back up in this system. Okay? But at least in this context, we were thinking about the galaxy, we can't wait that long. And so you will always get this catastrophic decay of the mean field. Although you do get a temporary growth, which is itself an interesting point here. On the other hand, if you put small amounts of this advective flux, before the alpha magnetic or the current helicity goes to back react on the magnetic helicity, on the kinetic helicity, it's advected away from the system. And because of this, the alpha kinetic survives, and you get up to fairly reasonable values of the mean magnetic field. In this particular context, if you put too much advective flux, because this advective velocity is there in the mean field equation itself, you will throw out the baby with the bath water. That's the expression, right? You want to only throw out the dirty water, but you may throw out everything. Because you will throw out the mean field itself, and which is bad for the mean field dynamo. So what is shown, for example, in the insert is, as you increase the advection, you will just decay the whole thing. The mean field fluctuates, everything goes out of the system before the dynamo can amplify it. Okay, this is a 1D, 0D solution of the same thing. Now you can see all R's coming in here, because Anwar is only involved here. Okay. Before I wind up, there are other helicity fluxes which have been calculated. One of them is the one due to Vishniak and Cho. And as I said, these other helicity fluxes depend upon the electromotive force, tensorial part of the electromotive force. The advective flux did not depend. It only depends on the mean velocity. And so the tensorial part of this electromotive force itself requires a closure theory to evaluate. So this is now depending upon a theory for this. And if you use such a closure theory, firstly you can show that if you have isotropic turbulence, then there are no such fluxes. If you have, for example, the velocity and the magnetic correlators to be, okay, not this. If you have completely isotropy in the turbulence, there are no fluxes. If you have a situation where the velocity and magnetic correlators are equal, there are no fluxes. But when you have shear in the system, this can break the isotropy. The shear in the system, can you introduce for you anisotropic pieces to the velocity? For example, the velocity will be affected by a term like u dot grad u bar in the presence of shear. And also, it can break the kind of cancelling effect between the velocity and the magnetic contribution. Because the magnetic field is also affected by the shear, but with a different sign here, plus here and a minus here. For example, in this paper we have done a simple estimate of this Vishniac-Kanchov flux, which he also did. He did also in his paper, but we made an estimate based on these equations. And you get this term, this kind of a term, which Axel likes, but I find very difficult to understand. But he can explain to you that if this is a shear tensor, okay, and you dot it with the magnetic field, mean magnetic field, cross it with the field itself, this Vishniac-Kanchov flux is proposed, it goes in that direction. So you say it goes down the shear or something like that, right?
Along the lines of constant shear.
Along the lines of constant shear. So you should ask Axel what he means exactly by this. I always find it difficult to explain what you mean by along the lines.
It's the same direction as the dynamo wave goes,
Uh-huh.
which also goes along these lines.
Okay. Okay. So now this is a flux, helicity flux, which is non-trivial completely. It depends upon the fact that there is a mean field. These twists are being transported in some directions, guided by the shear and the mean field. Okay? And it owes its existence completely to the anisotropy of the fluctuating field. If everything was isotropic, you will not have this flux at all. And it works to enhance magnetic fields. We have found in our mean field kind of models of this that it needs a finite amplitude field to begin with. It also is something which can blow up. Okay, so there are again some results from a paper with Sharanya and Anwar, and I think there are corresponding results in my paper with Axel. But in fact, this flux introduces an interesting thing that if you have sufficiently large shear, the mean field can in fact blow up. Okay? And in fact, this is a feature which tells you that you have not included all the effects of Lorentz forces, of course. They only included the bit due to the fluctuating field. The mean field itself, when it becomes strong, will lead to suppression, the normal quenching of many of these kind of fluxes, or all turbulent coefficients are likely to be quenched when the mean field itself becomes strong. And that has not been included at present. So I think I should wind up and just leave you with some thoughts. In these set of lectures, I have tried to bite the bullet, so to speak, and stirred up some amount of discussion. Because what is interesting in real astrophysical systems are that some of your maths is correct, but you want to guess the rest of your maths, and you want to make progress. So if you just stick to pure, everything being exactly correct, everything being precise, you will actually make no progress. It is good to be wrong and make eventually a progress than not make progress at all and be right all the time. So this has been my philosophy in this lecture. So there are many points which you will see are still controversial about mean field dynamos, about helicity, about the way we are using these fluxes. But these are things which are still alive and still growing, and it's my aim to expose the younger people to this stuff so that they start thinking about these issues a little more. And as you can see, I already consider myself fairly old. No longer a spring chicken, so to speak.
Spring chicken.
I was told that long time back. So these are the things which I have to say, that mean field dynamos at large RM have to work in the presence of strong fluctuations. And I was trying to tell you by simple examples that there are places where it works, and we hope that it works when we do not have all the restrictions which I mentioned. I've also been trying to tell you that mean field dynamos will have to work with helicity fluxes. And I've been trying to convince you that there is a need to define a gauge invariant description of helicity density and its flux. So these are things which I've tried to sell to you. These are things which you have to work out. It's very interesting that however high a redshift that we can see right now, galaxies have almost the same inferred strength to the magnetic fields as we have for the local galaxies. Not that we see very far in redshift. We see now, let's say redshift of 1, definitely there is some evidence from Faraday rotation measures, and there is also evidence of redshift 2 or something. So whatever galactic dynamo that Anwar is going to build during his next few lectures have to work efficiently at some level. And you need to think about this more and more. You'll find that the dynamo community will get coupled to the cosmologists. That will be one direction in which it will go. Because the cosmologists so far have completely ignored magnetic fields.
Not yet. I mean, a lot of them are troubling with this already for a decade. Many of them are working.
Yeah. I mean, the standard structure formation cosmologists.
Oh, those, yeah.
Yeah. I mean, cosmologists, you see, I should not hold forth on cosmologists. The important question which I have not addressed very much is the dynamo saturation for fluctuation dynamos, or to calculate these things really properly at high RM and high Prandtl number. And I have not at all said anything about primordial fields, otherwise Anwar will kill me. Maybe not.
I don't know, little bit.
You'll say something. Oh, okay, then I can kill you. And I think you should all look out for this radio telescope eventually, if you are thinking about the large scale magnetic fields, and all its precursors which are coming on. This SKA is a square kilometer array. So this is supposed to be one of the most challenging instruments with a collecting area of 1 square kilometer, with large frequency ranges. And they have 5 identified main projects. And one of them, to our good thing, is the origin of cosmic magnetism. So it stands equally with finding life in the universe, right? Or cosmology. So and the simple thing which they are going to do is to measure some zillions or millions at least, several million rotation measures throughout the sky. This is the aim. And so you will probe all the lines of sight that you know very closely. You will get magnetic fields in galaxies, in clusters, in intergalactic medium, wherever you want. Your eyes will just see magnetic fields. Or the SKA eyes will see this. And so we should be prepared for surprises, and I will stop.
Thanks, Anwar, for your lecture. Any questions, please? One curious thing, you pointed out, of course, that the U cross B bar in your correlations never trouble you. But if you do the second order correlation approximation, then you never can throw those away. They actually stay.
You mean U bar cross B?
Yeah.
Yeah, of course. You can never throw them away.
Under Soka, because you are not working with the time evolution equation, you are working with the... It's curious.
No, which one?
Karl-Heinz has
Sorry,
an answer to that?
which one? Which correlation? Sorry, I didn't get you.
U cross B correlating averaged, correlating with the calculating
Okay,
quantity.
okay. Yeah, Karl, yes, you have something to say.
I would like to make two remarks to this problem with alpha and kinetic and magnetic power. I will not give you the impression that I always fight against this relation. I think it is reasonable for a large region of cases, but it is not the full truth. First, if it would be very general, then it had to cover the case or the cases which you can treat in the second order correlation approximation. In the second order correlation approximation, the assumption you make is very clear, small velocities, then you can neglect all nonlinear terms. And then, as a result, in the second order correlation approximation, you get alpha at a given point in space and time is not equal to u at this point times curl u at this point, but also the spatial surrounding of this point is of interest, the behavior of u in the spatial surrounding, and in the history. And you can turn it as you want. You can never make an agreement between this formula u gave, which is in that sense local, and the non-local relation delivered by the second order correlation of approximation for alpha. Another point.
Yeah, I would say that the tau that you are putting here in all these things,
Sorry?
you can either put it in that way, or you can say that tau that you are putting, the tau, you say you have a general relation which is non-local, and you put the result equal to alpha times tau, and all this non-locality is put in the yes,
tau.
provided the tau is small enough.
Okay.
Provided the tau is small enough, right? So I never have any disagreement with you about the small magnetic Reynolds number, because we cannot.
Okay.
We cannot have disagreement because you can do everything exactly. And then you cannot have disagreement. I'm only saying that when you want to go, you cannot use the intuition that you always get from the small magnetic Reynolds number and extrapolate it to high magnetic Reynolds number. Always. Sometimes you can. This non-locality may be there, but when you have small correlation lengths and small correlation times, you will be able to pull it out. That's all. But we know, for example, in the presence of shear, even then it is very difficult to pull it out. You need to deal with integral equations.
Yeah, that maybe is another comment.
A second remark. You remember in my lecture I mentioned that in the case of MHD turbulence, an electromotive force is possible which is independent of the magnetic field.
The fluctuation diagonal
by Yoshizawa.
Yes. The battery, yes.
Mm-hmm. If you say in your equation for dE over dt, you have a magnetic field dependent term and a term you called n. And then you said, I require that this E tends to 0 if the magnetic field is 0.
Yeah.
And
I put u bar to 0 right in the beginning, of course. Yes.
By putting n equal to minus E over tau.
But you could consider a situation where u bar is 0. And then you don't have that.
About u bar. No. A turbulence without u bar. Say, and if you put your n equal to minus E over tau, then E tends to 0 if B is equal to 0. But you should get, in this case, this electromotive force.
Yeah, but the Yoshizawa term, right? That depends on small u dot
b. You don't get it in this way. Of course, you can make a trick and can say, okay, your n is equal to E minus E0 over tau, and then you get it as a stationary. So
but isn't it depending on u bar, the Yoshizawa term?
The curl of U-bar.
No,
curl of
no,
U-bar.
Curl of U-bar. So if you
for
put
example, in
the Yoshi, Karl-Heinz,
Yeah.
doesn't that term depend on the U-bar?
you can have it in two situations. One, if you have a mean velocity, and then this term is proportional to the curl of your car.
Yes.
You can have it in a turbulence where you have no mean motion, but you have the influence of Coriolis forces. Then it is proportional to the angular velocity, which defines this.
But then it's omega cross j, I thought.
Sorry? No,
You see, I have put, in that derivation, I put U bar to 0. So will you get such a term with U bar equal to 0?
But you also don't consider the possibility that the turbulence is under the influence of Coriolis force.
Yeah, I put everything to 0. I'm just putting, see, from what closure you have to make in the most general case, I have no idea.
As long as you restrict yourself to homogeneous isotropic turbulence, all is okay. This effect cannot occur in an absolutely homogeneous isotropic turbulence.
Yes.
But if you apply this procedure to the case where you have an anisotropic turbulence, for example, under the influence of Coriolis forces, then you run into this difficulty. You can, again, make a trick that
You change your closures, you are saying. You can change your closure.
But, okay, it is at least not very general.
No, you see, as I said, if I were, there are two things which I said. In the beginning of my talk today, I said, these are things which I also won't understand. Right? That was my first apology. And in particular for the derivation of J dot B, I said, I'm going to tell you in 4 different ways, which means I don't believe any of them to be absolutely correct, but I do believe that there is something in this. Okay, that's the spirit in which I am saying this.
There's a range of cases where it applies.
Yes, and we certainly know that there is a range of cases where it applies. It's not that...
So you have seen that, I mean, one statement I thought was quite interesting that Kando made, and that was the fact that even though there is trouble with some of the expressions, they are still alive. So that means people are still fighting about these things, and and there's progress along the way, of course. And so as long as this is the case, I think we should observe this state of the art, and especially the spring chicken in the audience. So I think it's time for lunch then, and we are looking forward to Argus Elise's lecture here in the same room at 2 o'clock. Thank you.
Actually, I thought you were